Hello my friends, today we are going to discuss our new chapter is on hydrogen production from thermochemical process. So basically in this particular lecture or maybe in this particular couple of lecture series, basically we are dealing with that whatever the wastage of the energy basically we are getting or maybe we are doing, like that sun or maybe the tidal or maybe the wind. So basically that whole energy we are unable to utilize. So some portions it is utilizing for the mankind for our day to day life, but some energy we are wasting. So if we will be able to capture those wasted energy and then that can be used for the future energy generations. So basically as we know that fossil fuels or maybe some kind of petroleum products are going to be finished maybe within couple of years or maybe within a decade. So basically then we have to move to some kind of unconventional or maybe non-conventional energy sources in terms of maybe the solar energy, in terms of some kind of fuel cells. So basically now the scientists are tending to work on those kind of materials to generate some kind of non-conventional energy sources, so which we can utilize in near future. So basically this kind of advanced energy conversion systems such as water electrolysis, as I told already, fuel cells and metal ion batteries or maybe metal air batteries. So these kind of new technology are coming into the picture. So basically in this particular topic we are going to discuss about the hydrogen energy. So basically hydrogen has the highest energy content per unit of mass of any chemical fuel and can be substituted the hydrocarbon in a broad range of applications. Its burning process is non-polluting. So hydrogen, so if you go for any kind of petrol, any kind of diesel, gasoline, so if we burn they will generate the toxic gas in terms of carbon dioxide or maybe the carbon monoxide. But if we burn the hydrogen, it will not generate any kind of toxic gases which can be harmful to the environment. So production of the hydrogen and storing of hydrogen is the great challenge nowadays to the scientist. So basically how we can produce? So there are some methods. So in one of the methods is known as the thermochemical water splitting. So thermochemical water splitting, from the name itself you can understand. Say suppose I am having that water which is nothing but the H2O, and if I will be able to break H plus OH minus, then H that can be useful in the near future itself. So thermochemical water splitting uses high temperatures from concentrated solar power or from the waste heat of nuclear power reactions and chemical reactions to produce the hydrogen and oxygen from the, this is the main and this is the main, so from the water itself. This is a long term technology pathway which potentially low or no greenhouse gas emissions. As I told already, it is not going to generate any kind of toxic gases which can be harmful to the human being. How does it work? Thermochemical water splitting process use high temperature heats from 500 to 2000 degrees centigrade to derive a series of chemical reactions that produce the hydrogen. The chemical used in this process are reused within each cycle, creating a closed loop that consumes only water and produces the hydrogen and oxygen. So simple, what we are trying to do? We are trying to break the water molecules over there. So in this particular case there are two types, you can see that one is called the central receiver reactor tower with heliostats, another one is that modular dismounted receiver or maybe the reactor. So in this particular case what we are doing, the sunlights are coming, then we are concentrating the whole sunlight into the solar receiver, it is generating the high temperature over there. Due to that the water is splitting into two halves, one is the hydrogen, another one is in the oxygen. So example of solar thermochemical cycle. So scheme of a two-step solar thermochemical cycle based on metal oxide redox reactions. So basically the reactions by which we are breaking it into the hydrogen and oxygen is known as the metal oxide redox reactions. Here MXOI denotes a metal oxide and M the corresponding metal or lower valence metal oxide. In the first endothermic solar step, MXOI is thermally dissociated into the metal or lower valence metal oxide M and oxygen. So basically it is a two step process, one is the endothermic process, another one is the exothermic process. Then the concentrated solar radiations is the energy source for the required high temperature process heat. In the second exothermic non solar step, M reacts with water to produce the hydrogen. So, first case it is producing the oxygen and the second case it is producing the hydrogen. The resulting metal oxide is then recycled back to the first step itself. So, in this particular case what happened? We are having that concentrated solar energy. In this particular case it is coming to the solar reactor, where as I told already it is producing the oxygen, and then that M is again reacting with the water itself. The water we are injecting in this from particular point and it is generating the hydrogen. After that again this MXOY is going into the first case. So, that is the recycle process is going on, in which we are getting oxygen and hydrogen separately in two different equations. One is the endothermic reactions, another one is the exothermic reactions. Next one is called the sulfur iodine thermochemical water splitting. So, thermochemical water splitting is the conversion of water into hydrogen and oxygen by a series of thermally driven chemical reactions. How it is taking place? Say suppose we are having sulfuric acid H2SO4, right. So, it is breaking into the half oxygen plus sulfur dioxide plus water more than 800 degree centigrade when we are heating that particular materials. Then these two again reacting each other and they are forming the H2SO4. It is a reverse reaction basically. So, you can see that iodine plus sulfur dioxide plus 2H2O. So, basically it is coming from here to here, and then we are adding the iodine over there, so that it can produce the H2SO4 plus 2HI. It is less than 120 degree centigrade. Then 2HI, it is again coming into the iodine and the hydrogen, that is more than 300 degree centigrade. So, ultimately we are getting this hydrogen gas from here, and also H2O we can split into the H2 plus half O2. With a suitable catalyst, the high temperature decomposition of sulfuric acid achieves 10% conversion at 510 degree centigrade and 83% conversion at 850 degree centigrade. So, process. So, as I told already, so the sulfuric acid can be decomposed at about 850 degree centigrade, releasing the oxygen and recycling the sulfur dioxide. So, this is the number one equations if I take this is as a number 1. Then the hydrogen iodide can be decomposed at about 400 degree centigrade, releasing the hydrogen and recycling the iodine. So, basically in this particular case whatever the H2O and H2 is generating, they are reacting over here, and then that is coming in this particular picture, and we are adding the iodine and the reaction is taking place less than 120 degree centigrade. Again it is forming the H2SO4 and the hydrogen iodide. Then in this particular case actually what we are doing, we are adding the water. The net reaction is the decomposition of water into hydrogen and oxygen. The whole process takes its only water and high temperature heat and release the hydrogen. In this particular case it is generating the heat, high heat temperature, and the reaction is taking place more than 300 degree centigrade, and ultimately it is generating the hydrogen gas which is coming over here as a product. So, all reagents are recycled, there are literally no effluents. So, from this particular case effluents means we are not getting any kind of byproducts or maybe any kind of toxic gases which can be harmful to the environment itself. Now, gas separations needs in SI cycles. So, oxygen and steam removal from H2SO4 decomposition reactants, what are the benefits? Increase H2SO4 conversion efficiency, concentrate sulfur dioxide for the second reaction, reduce reactor size for the second reaction itself. If I talk about the sulfuric acid steam separations in a membrane process, in this particular case the benefits is less energy consumption than distillation, concentration sulfuric acid for the first reactions, reduce the reactor size for the first reaction itself, not into the second. And if I talk about the hydrogen separations and the purification process, what are the benefits? Increase HI conversion efficiency, concentrate iodine for the second reactions, reduce reactor size for the second reactions, purify hydrogen for downstream applications. So, from these particular slides we can understand that when we are using the oxygen or maybe the steam or maybe rather sulfuric acid or maybe the steam or maybe the hydrogen separation membrane. So, every time we have to use the pure materials over there, and we can increase or decrease the size of the reactor depending upon that how much quantity of the hydrogen I required at the later stage. So, by this way we can optimize the whole reaction process. Now, let us discuss about what type of materials are very useful, or maybe rather I can say that scientists are working on now to generate that hydrogen gas. So, basically we can heard about so many times that about the graphene, because it is a fantastic material, it is not about for the hydrogen. Basically nowadays the graphene is widely used for any applications, either it may be biomechanical, biomedical, anywhere, energy storage device, energy generation device, or maybe for some mechanical properties, or maybe polymer matrix composites, metal matrix composites, people are using graphene worldwide. Another material that is called the graphene, then graphitic carbon nitride, in short basically we are calling it as a GCN, then HBN, that is hexagonal boron nitride, then people are using the black phosphorus over there, of course they are converting the black phosphorus from the red phosphorus itself. Then this is also another wonderful material that is called the TMD, that is transition metal dichalcogenides. Then we are having some doped graphene like nickel doped or maybe the nitrogen doped graphene, and some other heteroatom doped graphene also now people are using. So, now I am going to discuss one by one into the subsequent slide. Now, first we are going to discuss about the graphene. So, graphene its discovery in 2004 by Gim and Novoselav using their famous Scotch tape method. So, simple they are having that graphite. What is graphene? Graphene is nothing but a single layer of the graphite itself. So, they are having that tape, first they have stick that material graphite onto that, and then after that they are pulling so many times, so that the layer by layer separation will be taking place, by which they have prepared the graphene material. So, graphene has become a leading research interested in various fields such as electronics, biomedical engineering and electrocatalysis, as I told already. And here also whatever the materials we are going to discuss, that basically are acting as a catalytic material or maybe the catalyst, so that our hydrogen generation can be enhanced. So, graphene is a one atom thick 2D carbon crystal, as I told already, in which sp2 bonded carbon atoms are packed in a hexagonal lattice resembling a honeycomb structure. This is the hexagonal structure of that graphene. So, it is having total 6 carbon atom together. It is considered as the fundamental building block for other dimensional carbon materials, including 0D fullerenes, 1D carbon nanotubes, 3D bulk graphite or other carbon architectures. It depends. So, either it can be 1D, it can be 0D, it can be 3D, depending upon that which x, y, z, which direction are into the nanometer range. So, when we are talking about that 0D, that means all the sides are into the nanometer range. If we talk about the 1D, so 1 is into the macro scale, either it may be the micron level, and rest y and z or maybe x and y or maybe the x or z are into the nanoscale. So, like this way we are classifying the whole materials into the 0D, 1D, 2D, 3D directions. The cause of such interest in graphene is due to its many unique properties, such as high theoretical surface area like 2630 meter square per gram, high modulus of elasticity, that is almost 1.0 terapascal, and good thermal, that is 500 watt per meter per Kelvin, and electrical conductivity is almost 106 Siemens per centimeter. So, basically this is the wonderful properties of the graphene, that is why people are widely using for every applications. Now, let us discuss on to the second material, that is called the graphene. So, graphene is another allotrope of carbon, that is a one atom thick planar sheet of sp and sp2 bonded carbon atoms arranged in a crystal lattice. So, one is the sp2, 6 atoms over there, and then they are attaching with the sp bonding over there. So, that is why it is called the sp2 sp bonded carbon atoms comprised of benzene rings. So, this is the benzene rings, sp2 like carbon atoms, whatever I have already told, and acetylene sp like carbon atoms linkers. Graphines were named after their relationship to graphite and the acetylenic compounds. They are differentiated as graphene or maybe the graphene in figure, graphene etc., based on the number of acetylene groups between two adjacent benzene rings. So, in between two adjacent benzene rings, that how many are attached, whether it is single, double or maybe the triple one. The synthesis of 2D graphene is mainly based on bottom up methods such as CVD, chemical vapor depositions, and gas liquid or maybe the liquid liquid processes using hexaethynyl benzene as a precursor monomer. In the third one, we are going to discuss about the graphitic carbon nitride. In short, basically we are calling it as a GCN. So, carbon nitride is one of the first artificial polymers reported in the scientific literature. Graphitic carbon nitrides, as I told already, basically we are writing is like a GC3N4 is a 2D crystal with a van der Waals layered structure and is considered to be the most stable allotrope of all various carbon nitride materials. Analogous to graphene, the crystal structure of GC3N4 can be described as a hexagonal carbon framework with a N substitute carbon through the sp2 hybridization of carbon and the nitrogen atoms. So, now you can see in every alternative there is one nitrogen atoms are present. So, if we talk about this one, so suppose if I cut this particular side, so what will happen? Here I am having 3 carbon over there, right. So, that is why it is C3 and nitrogen 1, 2, 3 and 4. So, N4. So, that is why it is coming the C3N4 structure over there. Two structural isomers of GC3N4 exist and are synthesized using different precursors and condensation methods. Next, fourth one is called the hexagonal boron nitride. So, basically we are calling it as a HBN, is another analog of graphite and is also known as white graphene. Bulk HBN has a layered structure with lattice constant of 2.50 angstrom and interlayer distance of 3.33 angstrom. Differing from graphene, HBN is an insulator with a thickness dependent band gap. So, now in electronic and optical devices, HBN nanosheets have been used as dielectric substrates for graphene and molybdenum sulfide based heterostructure because it is having a wide band gap. However, pristine HBN displays barely no performance for electrocatalysis, limited by its poor conductivity and poor catalytic activity. So, that is why people are trying to modify the HBN by some doping or maybe the coating or maybe some kind of incorporations of the impurity inside it, so that it can act as a good conducting material. Next, fifth one is called the black phosphorus. So, basically the black phosphorus, in short we are calling it as a BP, has a 100-year long history as its bulk from was first synthesized in the year of 1914. BP is layered semiconductor with an orthorhombic crystal structure. One phosphorus atom is covalently bonded with another 3 to form a puckered honeycomb structure in a single layer. So, basically this is the structure of that black phosphorus. The 3 bonds take up all 3 valence electrons of phosphorus, resulting in a band gap of 2 electron volt, which can be tuned by controlling its thickness. However, only a few works have been reported about its applications in electrocatalysis, which may be due to its low stability under electrocatalytic conditions and poor electrical conductivity. So, that is also the another drawback for the black phosphorus. Then the sixth one is called the TMDs or maybe the transition metal dichalcogenides. TMDs can be described with a metal chemical formula MX2 basically. So, WS2, WAC2, MOS2, MOAC2. So, these all are the examples of the TMDs or maybe the transition metal dichalcogenides. M is a transition metal element and X is a chalcogen such as sulfur or maybe the selenium. Bulk TMDs consist of monolayers stacked by van der Waals force, whereas the general crystal structure of a TMD's monolayer can be described as a sandwich structure, where one layer of transition metal is situated between two layers of chalcogen. So, XMX. So, that is why it is basically the MX2. A unique feature of 2D TMDs is their multi-crystal structure. For example, 2H hexagonal, 1T trigonal and 3R, that is rhombohedral, are the three common crystal structures of MOS2, which are dependent on the different coordination model between the molybdenum and sulfur atoms and the stacking order between the layers. So, basically that depends upon how you are arranging your materials over there. So, basically this is the chalcogen one, sulfur, selenium and the tellurium, and this is the transition metals over there. Next, seventh one is called the nitrogen doped graphene. N-graphene is the most studied graphene based electrocatalyst due to its simple synthesis process and relatively good electrocatalytic performance. Nitrogen is of similar atomic size to carbon, but it is more electronegative. Therefore, doping with nitrogen can change the electron configuration of graphene while minimizing the lattice mismatch after doping. So, that is why the people are doing the nitrogen doping onto the graphene. Being the earliest studied and the most important metal free electrocatalyst for the ORR, N-graphene has demonstrated some unique characteristics compared to metal based electrocatalysts. N-graphene has tolerance to the fuel like methanol and carbon monoxide present in the anode chamber of fuel cells, which largely prevents the crossover effects, because while doing that these kind of gases are generating which can react with the electrode, but in this particular case that N-graphene does not have any good reactions with the methanol or maybe the carbon monoxide. That is why that N doped graphene can sustain for a longer time as a electrocatalyst material. Then the last one is called the other heteroatom doped graphene. Besides nitrogen, other p block elements like boron, sulfur, phosphorus have been doped into the graphene matrix by physical or maybe the chemical approaches. Similar to nitrogen, the differing size and electronegativity of these heteroatoms to carbon can also be induced electron modulation, which changes the electronic properties of pristine graphene. These kinds of electrocatalysts can usually be prepared by annealing graphene oxides with the appropriate heteroatom containing precursor at high temperature, that is more than 900 degree centigrade. Basically, we are doing the doping. The doping level of these materials is normally lower than that of N-graphene. Doping graphene with heteroatoms either higher or lower electronegativities than carbon, that is psi is equal to 2.55 such as N, psi is equal to 3.04, boron 2.04 and phosphorus 2.19 can induce electrocatalytic ORR activity through intermolecular charge transfers in the graphene matrix. Actually, basically the doping is taking place by two methods. One is called the interstitial doping, another one is called the substitutional doping. So, whatever the doping materials you are going to introduce, that diameter is, if it is equivalent with the carbon diameter, then the substitution will be taking place. If it is larger, then the interstitial will be taking place. So, in this manner it depends that which type of doping will be done onto this graphene material. Now, let us come to the advantages. Water is an attractive feedstock since it can be recycled back into nature indefinitely. It is true. So, when we are making it into the hydrogen and oxygen, and then later stage this again hydrogen oxygen comes together and they are forming the water. One side benefit of a nuclear reactor that produces both electricity and hydrogen is that it can shift production between the two itself. Now, of course, there are certain disadvantages. What? That efficiency and durability of reactant materials for thermochemical cycling needs to be improved, because the efficiency is not up to that much level. Efficient and robust reactor designs compatible with high temperatures and heat cycling needs to be developed. Yes, because that reactor materials also should sustain at that particular higher temperature and the pressure. For solar thermochemical systems, the cost of the concentrating mirror systems needs to be reduced, because they are very costly materials. Now, we have come to the last slide of this particular lecture. So, in summary we can say that hydrogen has highest energy content per unit of mass of any chemical fuel. That is why scientists, researchers are nowadays tending towards the hydrogen generation and the hydrogen storage. Thermochemical water splitting uses high temperatures to produce hydrogen and oxygen from the water. We have already seen through that we are breaking it into the oxygen molecules and the hydrogen molecules, so that we are getting plenty of oxygens and the plenty of hydrogens too. The chemicals used in the process are reused within each cycle, creating a closed loop that consumes only water and produce hydrogen and the oxygen, because that is a very good environmental process for the society. The SI cycle has significant conversion at much lower temperatures. Graphene is considered as the fundamental building blocks for other dimensional carbon materials, though we have discussed about so many materials as a catalyst, so that the hydrogen or maybe the oxygen production will be increased. For solar thermochemical systems, the cost of the concentrating mirror systems need to be reduced, so that we can use that mirrors frequently to generate the hydrogen gas in the near future. Thank you.